CDB2 review, day, night, and seasons. It takes 1 day, 24 hours, for Earth to rotate, spin once on its axis, allowing for both daytime and nighttime. The axis is an imaginary line that runs through Earth's center. Would the North Pole or the South Pole receive the least amount of daylight hours? So looking here, would the North Pole or the South Pole receive the least amount of daylight hours? So right now it's in day, and we would say the North Pole would receive the least amount of daylight hours during this day because the North Pole or the northern hemisphere is tilted away from the sun, so the rays are less direct. The southern hemisphere or the South Pole would receive more daylight hours because the sun is more direct. They're in summer, they're having winter. It takes about 1 year, 365 and a quarter days for Earth to complete one revolution around the sun. It's Earth's tilt at that 23.5 degrees and the revolution around the sun that causes seasons. So, two reasons for seasons: the tilt of the Earth and the revolution around the sun. Seasons. The southern hemisphere and the northern hemisphere are divided by the equator. So summer in the southern hemisphere is going to have more hours of daylight and more direct sun because this hemisphere is tilted towards the sun. The northern hemisphere is tilted away from the sun, so it would get indirect rays, less hours of daylight. Summer in the northern hemisphere. So here in the northern hemisphere, it's tilted towards the sun. So we're going to have more hours of daylight and more direct sun. Here, your southern hemisphere below the equator is tilted away from the sun. So we're going to get less hours of daylight and less direct sun. It's winter. Which of these locations on Earth would experience the least number of daylight hours during the day? So it's day. So we would say, given here, the South Pole would be receiving the least amount of daylight hours because they're having winter. They're tilted away from the sun, where the North Pole would get more direct rays. Okay, so which of these locations on Earth would experience the least number of daylight hours? It's the South Pole or Antarctica. Which diagram shows the position of Earth when it's summer in the southern hemisphere? So we're looking the southern hemisphere, the part below the equator. So here the southern hemisphere is tilted towards the sun. So diagram B would be summer in the southern hemisphere. Here neither is tilted towards or away, so that's in an equinox, but that's incorrect for it to be tilted in that position. Same here, this is incorrect. So looking at D, maybe we can answer 3. Which diagram shows the position of Earth when it's winter in the southern hemisphere? So your bottom part below the equator is the southern hemisphere that's tilted away from the sun. So we are having winter. Phases of the moon. The moon goes through 8 phases as it revolves around Earth. Okay, you always want to have the new moon in between the Earth and the sun, and you want to go counterclockwise in revolution. So the phases, if you're a person on Earth and you look up at the moon, you see these phases due to the moon's position and the sun reflecting off the moon. New moon is where you see zero illumination, and then you wax in illumination until you're full. Then after a full moon, you wane, you lose that illumination. Okay, when we wax, we get the light on the right-hand side of the moon. So we start with a waxing crescent, first quarter, waxing gibbous, then we're full. We wane. So we wane a little bit at a time and we lose the light on the right. So we have a waning gibbous, third quarter, waning crescent, new moon. Every moon phase takes about 7 days. So if we go from a new moon phase and we want to count 1, 2 phases, it takes 7 days to go from a new moon to a first quarter. If we're a first quarter and we count 2 moon phases, 1, 2, that takes 7 days to go from a first quarter to a full moon. Okay, which phase of the moon will occur about 1 week after the first quarter? So here's the first quarter, and 1 week would be a full moon. You could also say that every quarter phase takes about 1 week, and you have 4 quarters: 1, 2, 3, 4. Each of the quarter cycles takes about 7 days. Again, so from the new moon to first quarter, that's a week. First quarter to a full moon, that's a week. Full moon to a third quarter, 1 week. Third quarter to a new moon, 1 week. Or we say every 2 moon phases take 7 days. If you're not on one of those major phases, new moon, first quarter, full moon, third quarter, and say you're on a waxing crescent, if you're on crescents or gibbuses, you just have to count 2 moon phases and that would be a week. So if I'm a waxing crescent, I count 1, 2. In 1 week, I'll be a waxing gibbous. If I'm a waxing gibbous, I can count 1, 2. And in a week, I'll be a waning gibbous. All right, let's name the phases. So when I wax, okay, so let's envision a new moon. That's when the moon is in between the earth and the sun. When you look up at the sky, you see zero illumination. When you wax, you slowly increase illumination on the right-hand side. So after a new moon, we have a waxing crescent because of the little sliver of a shape. Then we increase a little more and we're half of a moon, light on the right. So this would be a first quarter. And then more than half would be your gibbous shape, light on the right. We're a waxing gibbous. So new moon, waxing crescent, first quarter, waxing gibbous. Okay. And then what would happen is you would grow in illumination and then you're full. After a full moon, you wane and you lose the light gradually on the right. So we're going to lose a little light on the right, okay, but we're a gibbous shape, so we're a waning gibbous. Then we lose more. If we've lost half, we're a third quarter, losing the light on the right. And then when we lose more than half, we're going to be a waning crescent. So it goes full moon, waning gibbous, third quarter, waning crescent. So from the beginning, you have your 8 phases, 4 in your waxing, 4 in your waning. So new moon, waxing crescent, first quarter, waxing gibbous. Full moon, waning gibbous, third quarter, waning crescent. Name the moon phases in order. So here, when you have something in order, you have to look and say, okay, I'm losing light on the right, so I'm waning. If I'm losing just a little bit on the right, I'm a waning gibbous. Okay, and then when I'm more than half, or if I'm half, I'm a third quarter. Then more than half, you're a waning crescent, and then a new moon. And you can play this rap to help you memorize your phases. All right, let's look at tides. Okay, so here we have the sun, the earth, and the moon. Okay, so here you have your moon at a 90-degree angle. So if this was new moon, okay, in 1 week it would be a first quarter. So here when you have a first quarter earth and sun at a 90-degree angle, we say that that's a neap tide. Neap tides are where you're going to have your least effect on ocean tides because the moon's gravitational pull is pulling in this direction and then the sun's gravitational pull is pulling in that direction. So you don't really have a great difference between your high tide and your low tide ranges. Here on a spring tide is where you have the sun, the Earth and the Moon in a straight line. When you have a spring tide straight line, that's when you're going to have the greatest effect between tidal ranges, because you have both the Moon and the Sun's gravitational pull pulling on Earth's water in the same direction. So you're going to have really, really high tides and then really, really low tides. Okay, so that was neap tides at 90-degree angles. They both start with an N, neap and 90. Spring tide straight line. All right, important groups on your periodic table. Chemical reactivity. The number of valence electrons determines chemical reactivity of an element. The more reactive an element is, the more easily it combines with other elements to form compounds. The metals in group 1 are reactive nonmetals found, these metals are the most reactive metals on the periodic table. So let's have a look. These are the most reactive metals on the periodic table, and the most reactive nonmetals are going to be in group 17, called your halogens. Okay. And group 18 are your noble gases, and they are the least reactive. They don't react with anyone. They're inert, meaning they're not likely to react with other elements. So we have our most reactive metals in group 1, and group 17, our halogens, we have our most reactive nonmetals. And in fact, they react with each other because they have what each other needs. These guys just need one more valence electron from group 1. Okay, and we call these guys the takers. And group 1, we say they're the givers. They just want to give away that one valence electron. Let's highlight our noble gases one more time. In group 18, these noble gases do not react. They are the most non-reactive gases, referred as inert, and they're not likely to react with anyone because their outermost shell is full with 8 valence electrons. Noble gases. The 18 columns vertically up and down on the periodic table are called groups or families. These elements in the same group have similar chemical properties. So we can say in group 2, all of these elements vertically up and down have similar chemical properties. They're both going to have, they're all in group 2, so they all have 2 valence electrons, so they're going to react chemically. Similarly, they're going to do the same thing. They want 8 valence electrons and they only have 2. Elements in the same group react similarly because they have the same number of valence electrons. You may recall that valence electrons are the electrons found in the outermost energy level of an atom. So number 1 represents an element right here. What other elements would react similarly to this element? Well, you'd have to look on a periodic table and see what other elements are in the same group as this element number 1. So all these other elements would react similarly. Then going over here, same thing. If this is group 14, all these elements in group 14 have 4 valence electrons, so they're going to act similarly to element 2 in having 4 valence electrons. Which number represents an element that is least likely to react? So if you look at number 4 is found in group 18. Those are your noble gases. Those are the least likely to react. Okay, they're stable. They have those 8 valence electrons in their outer shell. All right, let me minimize and grab some web paint and help you with this problem. It says strontium phosphate is a crystalline substance used in medicine. How many total atoms are represented in one molecule of strontium phosphate? So this is one molecule because there's no coefficient in front of here. If we wanted to put a 1, we could and say this is one molecule, but we don't need to do that. When we don't see a coefficient in front of the chemical formula, it's one molecule, that one molecule we're looking at. So we want to count the atoms in this molecule. So I just brought this down so you can see it a little bit better. And I need to grab some web paint, which I do not see up here. Let me see if I can borrow this for a minute and use this tool. So first I need to know, well, what elements do I have? Each capital letter represents an element. So I see S, R, that's one element, and I want to know how many atoms do I have of that element. I also have phosphorus, okay, which is an element, and then I have oxygen. So I want to go back to my question, and your question is asking you how many total atoms, okay, how many total atoms are represented in this one molecule. Okay, so let's count them. Your subscripts are going to tell you how many atoms you have. A subscript is a smaller number after the element to the right. If there's no subscript, it's just one atom, that one that you see. Okay, so we want to kind of read this left to right. So if we look here, we have a subscript of 3, so we have 3 atoms of SR. Okay, now going over with your parentheses, what you have here is a subscript outside the parentheses that needs to be multiplied by the subscripts inside. So to understand how many phosphates I have to take 2 multiplied by that 1 phosphate. Okay, so I have 2 atoms total there. And then I would do the same for oxygen. Take that subscript outside and multiply it by the subscript inside. So 2 times 4 would give me 8 oxygen atoms there. So to get your total number of atoms, you'd have to add these all together. So 8 plus 2 is 10, plus 3 is 13 atoms total in one molecule, okay? Because again, a coefficient is a large number in front of a compound. This does not have a coefficient, so it's just one molecule, that molecule we see. Parentheses is just going to tell you that you have that part twice. So that's why we have to multiply that subscript by the subscripts inside, okay? Okay, let me just erase and see if I can move to the next slide without a problem. Okay, then going to our next slide, we're going to talk about Newton's third law. Okay, actually it's his second law where force equals mass times acceleration. So here we need to calculate the acceleration of the cart. So it reads, if all other resisting forces are ignored, what is the acceleration of the cart? So you're going to be given the formula of Newton's second law, force equals mass times acceleration, and then you have to put that formula into the formula chart. Remember, multiplication goes across, so mass times acceleration would be placed here, and then your force would be above. If you cover up your acceleration, what you're trying to solve for, your formula reads force divided by mass. So now we have our formula, acceleration equals force divided by mass, and we simply plug in the numbers. We need to know what's the force acting on the cart. Now, this could be tricky because if you have one person pushing to the left with 30 newtons of force, and then you have one person pushing to the right with 30 newtons of force, you have to get your net force. So your net force is, if they're in opposite directions, you have to subtract. So 50 subtract 30, I have a net force of 20 forces acting on the box. So my force is 20, and then the mass of my box is 10. So 20 divided by 10 is 2. So my acceleration of the box is 2 meters per second. Okay? And then lastly, one question on balanced and unbalanced forces. It says a pitcher throws a ball towards a player holding a softball bat. The player uses the bat to hit the ball. The bat exerts 10 newtons of force on the ball. Describe the reaction force of the ball on the bat. So, for every action, there's an equal and opposite reaction according to Newton's third law. So if the bat applies 10 newtons of force to the ball is going to apply 10 newtons of force onto the bat. So we can say the bat will exert a 10 newton force on, the ball will exert a 10 newton force on the bat. Okay? So whatever force the bat hits the ball is going to hit back on the bat with the same amount of force. Okay, now it's time for you to show how much you learned. So you'll be taking your CDB. I hope that review was helpful for you. Good luck.